Okie dokie. Where is the share button? Here we go. So this paper was kind of interesting because when we type it in, we go to the first one, which is usually the one that it would tell us, like, is this a free paper? Is this not a free paper? I was looking at this as like, oh God, this is a paid paper. And like, that's one of my things is that I don't support like the paid ones. I only like read the open access ones that are free to access for anybody because this is dumb having to pay to access and read scientific papers. I'm completely against that practice. So I was like, oh man, I had this one posted. I thought this was free. I usually double check that before I like add it to the list. Um, and this is like where it's the journal it's published in. So I was like, well, shoot. But then I go back and I was just testing a couple because that's what I do. I just like check a couple different sources just in case there's a free one. And you don't see this very often, but the authors actually uploaded a free one. So usually you'll have to request to the authors to send you a free copy of their paper. And then you can use that. And then there's like certain criteria, like you shouldn't share it with people, et cetera, et cetera. So I try, if I ever do that, I've done it a couple times. I just acknowledge, like, this is what I was told. I'm not going to show it to you, but I'll read it to you. That way I'm not breaking any, like, I don't know if it's IP, but like I'm not getting into legal gray territory. But this one, you don't see this very often where you have an author uploaded thing free on a site, Airbox America, while it's being paid on another site. That's usually bad practice. But yeah, so, well, we got a free copy of it. So I'm not going to knock it, but I guess allow. There we go. Okay. So let's zoom in. Yeah, so the reason I'm doing it today on Monday is I took some PTO off on Friday and today so that I could just recover or relax and not get burnt out for my job because I was starting to feel a little bit of burnout. So I was like, I'm going to take some time off. So I took some time off Friday, Saturday, Sunday, just basically recovered and then feeling back to my normal self today on Monday. So that's why I'm doing it today. So sorry that people aren't going to be able to watch it live, but you can definitely watch the recording, and I hope you do. So this is the one that was voted on by the. So a couple people voted, but like the paid members get preferences. So the paid member got their choice, their selection here, which is contextualizing equivalent clean airflow rates for airborne pathogens of ionizers and other electronic indoor air cleaners. So this can be a couple different things. So I'm going to see what it is first before I jump in to explaining what this is. But they're basically saying equivalent clean airflow rates. So they're testing different sterilization methods through HEPA filtration and other methods using the same airflow rate of a room of the same size. So it's just switching out one-to-one. Here it looks like typical HEPA filter devices, and then over here there's 45 ion ROS generating devices. So ROS is typically reactive oxygen species, which in our bodies is a no-go. We don't want that. Reactive oxygen species, if this is the same thing we'll see in the paper, is basically an unpaired oxygen molecule within a system. So it has like a negative electron that's free, so it can readily bond with something else. So in our bodies, we don't want that, because if we have free oxygen radicals randomly bonding with things and creating reactions in our body, that's going to be a bad thing. So this is typically a negative thing. But I guess what they're saying is a controlled level, and it's not going in people's bodies. Maybe this is something that could like bond to viruses like SARS-CoV-2. Looks like they have some COVID viruses floating around up here, and then some bacteria, the green. So these are typical. Right here, this is a typical bacterial drawing. It's got like the little squiggly arms and then a tail. Usually you just have one or the other. You don't have both. But, artist's choice. And then we have COVID spike proteins here. So we've got some sort of unit up here that's creating reactive oxygen species. I don't think that's probably, this is what I think it is, RS. I don't think this is a good thing necessarily, because we don't want these to go into our bodies and cause reactions. Be a very negative thing for us as people. And then we have some sort of box down here. So I don't know what this is. I don't know if this is, we'll figure it out as we read through the paper. So for the abstract, additive electron, first over here. So with the equivalent clean airflow rates, we have typical HEPA filter devices, and it has this big range from 100 to about 650. And then 45 ion ROS generating devices, it's down here. Looks like 50 to 100 clean airflow rate, so meters cubed per hour. This is very small in terms of space. This can get very large in terms of space. So it might be showing that it's not like great for cleaning a full room, because it can only really work for small rooms and small spaces. But yeah, again, this is all just speculation from the images before we jump in. So additive electronic air cleaners like ionizers, photocatalytic oxidizers, and plasma devices intentionally release reactive species into indoor air so that they may inactivate infectious airborne pathogens. So it is going to be reactive oxygen species. So these unpaired oxygen electrons that can bind to things and then disrupt membranes and stuff like that. Very negative on our bodies, could be beneficial for bacteria and other pathogens, viruses, bacteria, fungus, etc., parasites maybe. So third-party commercial testing and peer-reviewed studies alike typically report inactivation metrics in terms of percent or log reductions observed from chamber experiments. Typically, either or, that imply a nearly complete elimination of infection risks. However, those metrics are highly dependent upon the experimental volume and duration. So it's saying how big the space is and then how long the whatever you're using is active. So they do not directly translate to actual effectiveness indoors. That's not true. So authors are making some pretty strong claims right off the bat. We reviewed 45 experiments across 14 published studies and converted reported reduction metrics into equivalent clean airflow rates, ECA. Different studies yielded distinct ECA distributions, suggesting that differences in experimental procedures, device specifications, or environmental conditions may be more important equivalent clean airflow determinants than the target pathogen or the underlying device technology. Study averaged ECA equivalent clean airflow rates span between 1.4 and 134 meters cubed per hour, with the median study having an average equivalent clean airflow rate of 31 meters cubed per hour. Even small off-the-shelf HEPA filter air cleaners typically provided equivalent clean airflow rates that exceeded the best performing additive devices analyzed herein. So it's saying that HEPA is better than the alternative. HEPA filters, even a off-the-shelf one, is going to be great. Is what this is saying. So that's what this chart over here is showing, is that any off-the-shelf part, even your lowest performing HEPA filter devices, are going to be more effective than your ion reactive oxygen species generating devices. And I guess this is what this orange thing is. So it's showing the two different methods. So one is HEPA filter down here, some sort of air filtration device, and then the overhead air filtration device up here. So it's saying that the HEPA is superior. And we know that things like Corsi Rosenthal boxes, things you can make yourself with box fans and HEPA filters, MERV 13 or above. So it goes all the way up to MERV 18, MERV 21, I think. But anything above a MERV 13 or a HEPA filter would be good. if you want to install those either in your HVAC units for your house, or if you have like an apartment or something, a Corsi Rosenthal box would be great for that. I have 2 of them myself. They're low efficacy, even small off the shelf HEPA filter air cleaners typically provide equivalent clean airflow rates that exceed the best performing additive devices analyzed herein. They're low efficacy relative to alternatives, environmental factors that can affect performance, and chemical byproduct concern. So, like the reactive oxygen species, chemical byproduct concern for that is the fact that not only will it harm bacteria and pathogens, but it could also harm us if we breathe in a significant quantity of these, or if it really just comes into contact with things like our eyes and our membranes. Those can be bad for us as well, because we are also made up of cells. They're are discussed in the context of test standard development and system selection. So the need to rid indoor air of infectious pathogens has risen in saliency since the COVID-19 pandemic. Saliency just means importance. Dedicated air cleaning that supplements outdoor air ventilation is often desired or required. So this just means like clean air turnover. So bringing like fresh outside air into a space more frequently and taking the inside air, pumping it back outside is like desired or required. We should have higher air turnovers per hour. That's what that means, is having more air, clean, fresh air coming in from outside, and that air from inside going back outside is what we want. We want high rates of that. Media filtration can be highly effective when sized correctly, but this approach is limited by practical constraints associated with the fan power draw, noise, and air velocity. So, for instance, like in a room like this, with just one person, me in here, a single Corsi Rosenthal box is sufficient. It can be quite loud if I put it on the full setting. I usually have it at setting 1 or 2. And this is going to keep it at a low hum. So it's not going to be bugging me if I have it off right now because I'm trying to record and I don't want it to interrupt the vocals and have this like humming in the background. So that's an example of a drawback. And it can only do so much, but since I have it running all the time, it's going to be doing a lot over time. But when I have more people in a space, I'm going to need more filters, especially if it's a smaller space like this or even a larger space. So you're going to have to have a lot of those at set distances throughout a building. If you have a large building, which can increase costs, it increases noise, it increases electricity draw, things like that. And then like the burden of having to change out the filters over time, and like who's going to do that, and et cetera, et cetera. Electric air cleaners are a possible alternative to media filtration. So this is going to have something that's installed into like an HVAC system or something that's installed overhead that can clean the air by secondary means. In this context, electronic refers to the use of electric energy to release reactive oxidizing species into the air. So when there's a process called electrolysis, you can use this to do things like anodized materials, which is just basically like electrostatically go from a cathode to an anode, a positive to a negative charge. And then this can coat a metal to create like a colored surface. So like a purple, a green, a blue, a yellow is something that we typically do. And this gives it slightly different properties. That's typically what you would have most likely have seen if you've seen anything like that at all. But you can also do this in another way on a smaller scale to sort of, you have a positive and negative voltage that's passing through a medium like water, and you can generate chemical reactions within the water that create oxygen, water, and then unbonded oxygen, which is the reactive oxygen species. Typically, you'll have like H2O. You'll force break this apart through something like electrolysis, and then this will generate oxygen and then unbonded oxygen because chemical reactions aren't perfect. So you'll split the water into O2, O negative, which is the unbonded reactive oxygen species, and then sometimes even O3, which is a triple bonded oxygen. These typically happen in low quantities. So you'll have to like be repeating this process for a long time to generate enough reactive oxygen species to be able to like do this. Other things you can do, like hydrogen peroxide, you can break that apart and you can more efficiently get things like free oxygen radicals. But that has its own issues. But that's a little high level thing in those types of contexts. So in this context, electronic additive matter. So these devices are classified as operating in an additive manner. Wait, what? I missed a sentence. In this context, electronic refers to the use of electric energy to release reactive oxidizing species into the air. So these devices are classified as operating in an additive manner. So they're adding the free oxygen radicals to the space, to the air. Unipolar or bipolar ionizers, photocatalytic oxidizers, and non-thermal plasma devices are common variants of electronic air cleaners. The additive species may be either ions, so you could have hydrogen ions peroxide, so H plus, OH negative, and then O2 negative. So these are going to be like peroxide ions. When you split like H2O2, the hydrogen peroxide, you can get H plus, OH negative, and then sometimes like O2 negative, but that's going to be, it really depends. H2O2 is what they're breaking here to create this reaction, or reactive oxygen species. All of these are oxidizers, the H plus, the OH negative, and the O2 negative, which is why hydrogen peroxide, which I mentioned before, is usually a good thing to like break through these electrolytic processes. Yeah, right there. It's fun when I somehow work ahead and just, yeah, anyways. So like the hydroxyl radical, OH, or hydrogen peroxide, H2O2, the intended effect is for these species to react with the molecular structure of airborne pathogens, rendering them inviable. In contrast, subtractive technologies like media filtration, okay, so they're saying subtractive is like removing from the air. So this would be a filter. So like if you pass air through a filter and you have the contaminated like particles or your viruses and stuff, as they pass through like that HEPA filter, they'll get caught. So you're subtracting those from the space in the air. But then when you have additive, you're adding something to the air, like these radical oxygen species, or reactive oxygen species, and they're then doing things in the air to kill the pathogens. Additive electronic air cleaners have recently grown in prominence for many reasons. Their installation operation is less intrusive than ventilation, and filtration upgrades in terms of space taken, noise, pressure drop, energy consumption, and maintenance. But again, they're less effective from what we're seeing. They're often advertised to improve indoor air quality holistically by removing particles, gases, and pathogens. So this is one of those important things when you see holistic, like this being promoted as a holistic thing. This is something that should always give you a red flag, because you're thinking like, oh, people like naturopaths and other types of people that are trying to make money off of people that don't really know better, that are trying to like improve their health or improve their wellness through other means. They're typically predatory, trying to prey on people. So this is something that apparently people in those types of movements are trying to use and like put off as like this great thing. So holistically, by removing particles, gases, and pathogens, citing third-party tests, manufacturers often claim extremely high disinfection rates. And the problem here with what we're seeing here is that when you do equivalent clean airflow rates, it works only for very small spaces, for very small. So if you have like a room like this probably isn't even going to cover the whole space. It's only going to cover like maybe this section right here that I'm circling of the space. Here, I forgot I can drag and draw. So maybe like this section of the space, while the HEPA filter, the orange box, will take up the entire space. So if we're only cleaning air and disinfecting air like in this part of the space, then we're going to have very high disinfection rates up here, but very low disinfection rates for the rest of the space. So when you think of the whole space holistically, to make a pun, you end up having not as effective clean air in that space than you could have otherwise. And historically, there have not been Standardized testing methods or evaluation metrics for the removal of biologic contaminants by electronic air cleaners. In this absence, many experimental studies have reported impressive sounding inactivation levels like multiple log reductions and more than 99% removed. That suggests a greater impact in indoor settings than these cleaners can realistically achieve. These tests typically occur in controlled laboratory environments like sealed chambers, with the decay rate of an airborne pathogen is measured with and without the device in operation. A percent or log reduction compared to the control test is calculated after a certain amount of time elapses. This reduction metric is highly dependent upon experimental conditions like its duration and spatial volume. As such, the expected impacts in a building cannot be extrapolated from the reduction metric alone without additional context. A device that negligibly impacts real room pathogens can produce an arbitrarily large percentage reduction given a sufficiently long experimental time and or a sufficiently small experimental volume. So essentially what this is saying is that if you have this ionizer and you're having like this very small test space, test volume. Area is two-dimensional, volume is three-dimensional. So we're thinking of a room that's a volume that we're existing within. So if we have a small volume, like a container like this, and I'm testing this ionizer within this space, I could achieve a 99% reduction. But if I put it in a space like this, I'll probably only achieve like a 2% reduction. So that's one issue. And then also there's no like time limit. So that you don't have to like say, oh, within 1 hour, you should be able to kill like this much, this like log amount of pathogen, this percentage of pathogen. You should get it down to like 2% pathogen still alive after 1 hour. Well, they can just run the test for like 24 hours, 48 hours, a week and say like, oh yeah, we killed it within that time. So it's 99% effective, but they're not saying 99% effective within this volume over this small volume over like 2 weeks. And I'm just being like hyperbolic and dramatic about what I'm saying right now, but like that's essentially what there is when there's no standards. They can do whatever they want. And this is another great example. So remember a couple studies back that we talked about where they're talking about like using the MDCK, that cell line that they were using. I can't remember what the exact name was, but that MDCK cell line that was able to like take the pathogens in the air. You can use that as a measurement without this, and then do it within the space, like a room space like this, that's properly vented and controlled, and then have these cell cultures all throughout, and then measure it again with this thing working, and then you could see how that's impacting things over time. So that could be a really cool thing that people could do. Love science, love studies. This is how we can relate things to one another. So Stevens et al. First brought attention to the issues described above. Using hypothetical examples, they demonstrated how to convert experimentally derived reductions into either a clean air delivery rate, CADR, or an equivalent clean airflow rate, ECA. Both metrics are identical concepts that can specify the volumetric flow rate of pathogen-free air provided by either system or a standalone device. Thus, they describe a device's performance independently of room or test conditions. So it's basically normalizing these things versus with these calculations to one level or another level, and then saying like based off of this, we can compare like this device to that device or this HEPA filtration unit to that HEPA filtration unit. Which can help to fix some of these issues. It's not going to fix all the issues because you still have to worry about like test time, or actually, no, like here. So if we look over to the math right here, so we have a volume of your test. We have C test at time 0. So this is probably the concentration of the pathogen at test time 0. And then we have minus the concentration of the test at time t. So that's going to be the duration of your study. So this is going to be the volume of your space and the concentration of the test at time 0 minus the concentration of the test at time t. So that your study all over the integral from 0 to time t of the concentration of your test. And then this is going to be minus the volume of the concentration. Okay. So this is going to be a calculation that will give you the concentration of the test throughout your experimental design from start to finish. And then you're going to subtract the volume of the control at time 0 minus the control at times t. So this is not having your unit over the integral of the time from 0 to t of the control, the concentration. So basically the change in volume over the change in concentration of the pathogen, and then the change in volume over the change in concentration of the test with your HEPA filtration. Then without your HEPA filtration, you subtract that, and then you get a clean airflow rate. Whew, that's a lot, but that's essentially what the math is saying. And it's going to be in meters cubed per hour. So you're going to be using standard cubic matrix, even though most rooms, this is still cube. I was going to say some rooms aren't cubes, but mine is. And then some other calculations here. So ECA, the clean airflow rate, is the volume, is the chamber volume, and then we have K, which is 1 over hours. It's a first order pathogen decay rate constant, and control at time 0 and control at time t. Represent initial airborne concentrations of a viable pathogen at the start of an experiment and after an elapsed time. Subscripts indicate whether the cleaner was in use or not during an experiment. This approach assumes strictly first order decay, and that the lone data point at time t is representative. So first order decay is just going to be a linear decay. It's just not so. You can have different types of decay. You can have logarithmic decay. Well, I guess it would be going this way. So you can have logarithmic decay. You can have exponential decay, and then you can have linear decay. So this is first order. Well, I guess technically it would be 0th order is a constant decay, flat line. You have first order, which is a linear decay. You have second order, which can be like a parabolic decay rate. So it's going to be like a smooth curve like that, like a half U shape. And then you can have third order, which is going to be things like sometimes like exponential decay, logarithmic decay, some sort of like weird pattern. We don't do third order. A lot of times we'll only go up to second order most times. You can usually justify away third order. But anyways, that's what they're doing. This approach assumes a strict first order decay, and the lone data point in time t is representative. Other studies reported K directly. Only equation one was used in those cases. So this is saying how they calculated it for studies that didn't directly report this decay rate. However, biological inactivation by photochemical means often deviates from first order kinetics. So saying that it's going to be faster at times and then slow down. So conventional first order approaches for calculating the equivalent clean airflow rate fitting a log linear curve to a decay data may yield erroneous or biased results. So erroneous means error-based. Biased means there's like an offsetting essentially of the data. And Horatian et al. Developed an integral approach for obtaining a more accurate and generalizable steady state ECA metric, which is what I explained earlier. So this is going to be like how they can get some constants and some first order mechanics. This is second order mechanics. They're probably going to compare both of them together within the data. And then they plotted. So we have the equivalent clean airflow right here on the left. We have the reference studies here, and then the types of viruses that were tested within each study, with each method. So all the circles are going to be the different types of viruses tested. And then if we have a circle, it's going to be a BPI. If it's a square, a PCO, a diamond, a plasma based, and a triangle, and H2O2. So we have a triangle here, H2O2. Square is going to be PCO. Triangles, H2O2. Yeah, and then we have the average from each study. And then for a study to be included in the analysis, the following 4 criteria must have been met. One, they had to isolate its effect. The device must rely solely on electronic air cleaning rather than a supplement to filtration media. So they can't have like a combined thing like a filter and this electrolysis. This reactive oxygen species generation. Um, they have to have just that electrolysis or just the filters, like the HEPA filtration. Can't have both because then you can be artificially increasing the efficacy by having the filter kind of like leverage most of the weight there. Decay must be measured in a controlled environment, example, a laboratory chamber. Airborne pathogens must be the target contaminant, not particulate matter. So looking directly at viruses, bacteria, fungus type stuff. Particulate matter can be anything like dust or really anything that's small that can exist, which is not necessarily other like virus or pathogens, but it can be like volatile organic compounds or sulfur or surface pathogens. Oh, so surface pathogens. So they're looking at like just airborne stuff in the air, not like fomite. Browsing manufacturer websites, pragmatic searches on Google and Google Scholar with search terms including combinations of various air cleaner types, keywords of pathogens, viruses, bacteria, etc. So this is how they're looking through it for the review. Much of the peer review literature returned from online searches is investigated. I lost my place. Investigated underlying technologies such as photocatalytic substrates rather than the disinfection efficacy. Of the studies that did quantify disinfection, many measured surface disinfection rather than the inactivation of airborne pathogens. Some third-party laboratory reports are available from manufacturer websites directly. Others are discoverable from online searches, but many remain difficult to access. Thus, only 14 studies summarized in Table 1 were found to be suitable for inclusion herein, providing 45 unique decay experiments for which the equivalent clean air flow rates were able to be computed. Most studies investigated BPI or PCO. Did they define these at some point? BPI, PCO, BPI, PCO. BPI is bipolar ionizers. PCO is photocatalytic oxidizers. Two studies studied non-thermal plasma devices, and two injected H2O2 directly in lieu of analyzing a packaged air cleaner. 4 studies used commercially available products and disclosed their manufacturers. The challenge pathogens encompassed various viruses and bacteria, with bacteriophage MS2 being the most common one in this data set, followed by SARS-CoV-2. So the results in discussion, the calculated electronic air cleaner ECAs were highly variable, spanning about 2 orders of magnitude. 22% of the calculated ECAs exceeded 100 meters cubed per hour. One device's ECA was 283 meters cubed per hour. That's very high. But all others were less than 160 meters cubed per hour. Another 22% of the calculated ECAs were below 10 meters cubed per hour. So that's very low. That's going to be like your very small, off the shelf HEPA device. But none were less than 1 meter cube per hour, which would be incredibly small. It would basically be doing nothing. Three studies produced average equivalent clean airflow rates of greater than 100 meter cube per hour, with 134 meters cube per hour being the largest study averaged ECA. 8 study averaged ECA between 10 and 100 meters cube per hour, and 3 were between 1 and 10 meters cube per hour. Large variance geometric means were used to compute subgroup averages to contextualize these ECAs. Even small, low-cost, off-the-shelf HEPA filter devices intended for personal use usually have calculated air diffusion rates, CADR. I hate acronyms so much. CADR, clean air delivery rate. Greater than 100 meters cube per hour. Readily available HEPA filter devices sized for larger residential homes have clean air delivery rates between 500 and 800 meters cubed per hour. So that's like a reference, like for a whole house, they're going to have like 500, 800. So 100 meter cube would be like a fifth to an eighth of that size. So that's going to be like a room essentially, or maybe 2 rooms. When you have like 100 meters cubed per hour, just doing an off the dome napkin calculation. Meanwhile, custom built box fans, Corsi Rosenthal boxes, are capable of clean air diffusion delivery rates of greater than 1,300 meters cubed per hour. So this is saying that Corsi Rosenthal box are almost better, than the HEPA filters used for large residential homes. So these are highly effective. So definitely use them. The electronic air cleaners with the highest calculated ECAs herein are only as effective as small HEPA filter devices, which is what we explained at the beginning from the graph. Those on the bottom of our calculator distribution are about 1,000 times less effective than good HEPA filter devices or Corsi Rosenthal boxes. So they're so ineffective that you really don't even want to consider them. Germicidal ultraviolet irradiation, another possible supplement to ventilation filtration, has been shown to be a highly effective indoor air disinfectant if appropriately specified, designed, and implemented. One representative study measured approximately 50 equivalent air exchanges per hour of disinfection from a single 222 nanometer germicidal ultraviolet irradiation lamp in a 32 meter cube room. And if a high performing additive device that provides 100 meter cube per hour of clean air were used in this room, 16 of them would be required to match the GUV's performance. So this is saying that the 22 nanometers ultraviolet light could be incredibly effective. I still think, because we don't know too much about the safety and efficacy of these, they sort of got implemented like really quick. There hasn't been a lot of studies between them. If you're using a lamp, that means there's going to be a lot of direct contact of this light to your skin. From the studies I've read so far on it, it can cause a little bit of DNA damage, DNA methylation damage, and it can slow healing for people. These are two of the things that we found out so far. So I wouldn't necessarily like have this lamp in use. I think the best way that these are going to be integrated is by applying them to HVAC systems. So like we could install these inside of a Corsi Rosenthal box system, and then have some sort of like, I don't even know. We'd have to like have the box like hidden a little bit so the light isn't directly contacting people, or maybe the filters themselves would be enough to sort of diffuse the light so it's not directly harming people. So that could be a solution. But I think the ultimately best thing that is going to happen is installing these directly into HVAC systems, so that not only are you getting the clean air turnover rates, you're getting the high disinfection rates of the ultraviolet light. I think there's still, if you can swing it so that it's like installed within light systems above, sort of like at the White House, where it's high enough ceilings that it's not going to be directly shining on people. I think that could be a great use of it, but I still think there is quite a bit of concern and worry about having like a lamp that would be shining on you with this 22 nanometer light, because we still don't know enough about it. And the early studies are like very light. They're very light. They're like, oh, it's not going to damage your skin. But we've already seen that it can like slow wound healing. It does like it disrupts metabolic pathways within your skin, within the deep layers of your skin and like the surface layers of your skin, which gives enough concern that it's like, maybe don't do that until we know more about this. But this is showing how effective it can be. But we need to use it appropriately and in safe manners. The data set was examined to explore whether device types or specific pathogens influence equivalent clean airflow rates. While the statistical significance of device or pathogen-based patterns cannot be ascertained from visual inspection of the data alone, it appears that different studies often produce distinct Equivalent clean air distributions, for example, Lai et al. Study A and Jangre et al. Study L, both tested a plasma device on E. coli, but their ECAs differed by a factor of 28. That's very large. So that's 28 times difference in the equivalent clean air flow rates. Similarly, Peel et al., study 1, and Matsura et al., study M, tested COVID in activation with a PCO device and yielded average ECAs that differed by a factor of 13. So a little bit closer, but still 13 times different, pretty different. To quantify how the reference study, underlying device, technology, and pathogen each impacted the equivalent clean airflow rate in this data, we fitted an ordinary least squares model and conducted an ANOVA to compute each category's effect size measured by the partial W squared statistic. So you guys don't need to know this. This is just doing the stats. So here we go. So unipolar ionization may cause an accumulation of electrical charges on indoor surfaces, leading to an electrostatic discharge. That's another thing that can happen from this ionization process. So not only are you creating these molecules that have high reactions, while these highly reactive molecules that can also build a negative charge in the air. So when we have a positive charge, sort of like our bodies, we have a slight positive charge. We can create an electrostatic discharge, which could be problematic. Is another thing. You could like make a spark. Sparks can create fire. So it could be an issue in that sense. Certain exogenous reactive oxygen species exposures have been identified as causing adverse health outcomes. So this is what we talked about at the beginning, how it can be negative to our bodies to have these. And then also, like when you have like cleaning products in a house, like so we use like bleach and things, having these reactive oxygen species can generate like other things that can be negative to our health. So that's another thing they might not have considered in this. And the natural pollution that exists within our environment, so the volatile organic compounds, this can be like from uh, gases from outside, from like cars driving by, so exhaust coming into our house, maybe like from cooking and like giving off some smoke from the stuff. All sorts of things in our houses, like we have pollutants in our house at all times in the environment because of the world we live in. These reactive oxygen species can react with those. The companies claim like, oh, it's a perfect reaction and it's going to mineralize it, so it's going to make it a solid, and this will be completely harmless. They're saying it's mostly going to condense into carbon dioxide and water vapor. The science isn't well established for this, and we know from reactions that oftentimes they aren't like 100% efficient. Like nothing is 100% efficient. You always get byproducts. So while some degree of, they're saying like, well, some degree of this mineralization may occur and we produce like pure carbon dioxide, pure water vapor, the production of even more oxidized pollutants and ultrafine particulate matter has been documented in studies. So we know like this is not a pure reaction. And this can increase like the health hazards to people. And then additive cleaners are not the only interventions that chemically alter indoor air. So the 222 nanometer germicidal ultraviolet radiation, ultraviolet light, is another such technology. It may produce ozone and other oxidants that affect indoor chemistry. So when you have like ultraviolet light, it can cause excitation in molecules. So like when you have oxygen that's just existing in our air from the plants and everything else, this oxygen can get stimulated from the ultraviolet light, this high energy light, which is higher frequency. So it can energize the oxygen and cause it to break, and then create those reactive oxygen species. So while you're not, it's kind of like a light induced electrolytic process in a way. Um, and then this can create ozone within your house, and having like high levels of ozone in an environment can then be very harmful for us. Um, and for our environments as well, if this is used at a mass scale and we're producing a lot of ozone um, as a society, this could then be not great for us health wise. And then, however, but like despite this, 222 nanometer germicidal ultraviolet light can provide very high rates of disinfection. So more situations may exist where its benefits outweigh its risks for additive electronic air cleaners. Um, which is saying like there might be some situations in the future where this is like definitely like the go-to technology. I think it's going to be integrated with HEPA filters. I think that's where it's like gonna like do amazing things. Um, these results build upon existing evidence that additive electronic air cleaners are not strongly efficacious indoors. They don't function well as air disinfectants, and their net public health effects are unclear, which is a fancy way, a scientific way of saying they're not that great. They're overblown. There's enough evidence to say that the manufacturers are overrepresenting their claims. Um, but scientists don't like to shake the boat too much. They're saying this is what the data shows, and we're saying that this is probably not what the manufacturers are saying. This is data that goes against that, but they don't want to enter into like lawsuits or whatever with libel. And also, this is just a compilation paper. This is a review paper. This isn't like direct evidence. This is looking at the everything and finding the results. Get that clean real quick. So they can't make direct conclusions. They can make indirect conclusions based off of what their study results are. Oof. And then all right. Well, that I was just skimming through the rest of it. That's basically the whole study. It's saying that using HEPA filter devices, you can get high clean airflow rates with the top performing devices around like 600 meters cube per hour. The bottom performing HEPA filters off the shelf being at about 100. Remember that the Corsi Rosenthal boxes they mentioned are at 1,300 meters cubed per hour. So with a simple box fan and 4 filters, you can have better filtration than most things on the market right now, according to the study. You shouldn't really be looking at any ionizing, ion generating products. These are completely ineffective. The worst performing HEPA filtration devices on the market off the shelf are going to be vastly superior to anything you can get from those. And these are going to cause health impacts by adding things to the air that shouldn't necessarily be there. And they're really only effective for very small spaces, and our houses are generally not small spaces. So HEPA filters are going to be the way to go. They're saying that the ultraviolet light 222 nanometers is promising technology, but again, it's very young technology, so we don't know all of the hazards and harms. That work is still ongoing. That's something that sort of emerged in 2021 is something that could be viable for things like COVID. And the White House even went so far as to install ultraviolet lighting in the Situation Room, if I recall correctly. So, like, people have been early adopters of this technology. But again, it's still in its infancy in terms of how we understand it in the scientific process, which always means that we should be careful in using it and recommending it to the public because we don't know the full scale of the harms, such as does it react with oxygen in the air, create ozone or other sort of byproducts? Is it going to react with cleaners in your house and stimulate those to create byproducts that are hazardous to your health? The things that I have seen in terms of slower wound healing, that's not desirable. Having that on your skin, long-term exposures. Is this going to impact our vision? Is this going to impact um, other things like maybe skin cancer? We don't know. We don't really know the long-term duration effects. And then like the intensity effects of like how close it is to your skin. Uh, and like we've seen some evidence that it disrupts metabolic pathways. So like there's going to be a great avenue for this technology to be integrated into our lives and to help us not get sick. But just getting like a UV lamp at this point is going to be dangerous because we don't fully know the hazards and harms and how to mitigate for those hazards and harms at this point in time. So that's my soapbox. This is what we learned from this paper. I hope you learned something and have a great day.